The StarTree index is one of the cooler features of Apache Pinot. It's even obviously where StarTree, the company, got the inspiration for its name. It's a really cool thing that delivers some results that seem impossible in terms of performance. And I've got Sandeep Dabade back on the show this week to talk about how the index works, what it's applicable for, when it's not applicable, and some ideas in real-world cases of just how fast this thing goes. Let's listen in. Hello and welcome to another episode of the Real-Time Analytics Podcast. I am your host, Tim Berglund, and I'm joined again by my friend and coworker, Sandeep Dabade. Sandeep, welcome to the show.
Thank you, Tim. Thanks for having me.
Thanks for coming back. As I always say, it's the triumph of hope over experience. Always good to have somebody come back to the show. The last time you were on, we talked about capacity planning, and that was based on a blog post you'd written. And I kind of like some of the blogging you've done. There was another series of blog posts you wrote a while back on the StarTree index. Now, you and I both work for a company called StarTree, named after the index, but this is everybody should know there's a difference here. There's StarTree, the company. There's an index that Apache Pinot has called the StarTree index that is a part of the open source product. Sandeep, what's the StarTree index?
It's all well documented in our blogs, but I'll just quickly give you a high level understanding of what StarTree index is, right? Like typically we have traditionally in OLAP databases, there is a concept of pre-materialized view, right? Like where you are able to make it trade-off in terms of storage and achieve like extreme high performance or fast performance for your like OLAP kind of queries, right? A typical query pattern is like group by certain dimensions and get some metrics or aggregate metrics on or on a certain set of aggregate columns, right?
Mm-hmm.
So StarTree index is a pretty advanced version of that pre-materialized view concept, where it actually gives you that ability to make that trade-off between storage and performance, right? Like instead of pre-materializing everything, all the dimensions and all the metrics, you are able to decide how much you want to pre-materialized and how much you want to do the raw table scan.
There you go, because there's the historical approach to real-time analytics before there were databases like Pinot. You really had to pre-compute everything and stick it in some kind of serving layer, like a key value store that was low enough latency to be, well, in the serving layer, to be in the user interaction loop. And part of what Pinot is telling you is, hey, good news, you don't have to do that anymore. You don't have to define everything. You don't have to pre-aggregate everything. If you've got lots of dimensions, just go ahead and throw the query at the database. The database will figure it out. And that's true. And here's this index that lets you kind of set this slider of saying, sometimes there might be some query pattern that's really common and you need to be really fast. And it fits this template. And we actually will pre-compute some of that. And I think you're saying at the cost of additional storage because you have to pre-compute and store things. But you get that by adding an index in the table config, some JSON configuration, if you're not familiar with table config, rather than you doing all that mess yourself. Is that fair?
Yep, absolutely.
Nice. So, and as I understand it, so check me on this, but when I tell people about the StarTree index, I always say the pattern is if you are doing a filter and aggregate. So there's some metric and you're summing or averaging or whatever, you're computing some function on that metric. And then you've got some combination of predicates that might show up in the where clause. So it's like 2 or 3, and maybe they'll all be there. Maybe just one of them will be there. Maybe some combination of 2 or whatever. You pick a small number of predicates that might be there,
Right.
and a metric you're aggregating, and that by itself, that's a lot of analytics. Okay, that's a
Yeah.
very
Yeah.
common query, and that's the thing. That's the kind of query that we're looking to optimize.
Yeah. So you could have X number of dimensions, right? You can slice and dice by any combination of those. You can have Y number of metrics and then Z number of aggregate functions itself. So it's a combination of all those, is what you can pretty much now, all those query patterns comprising of those dimensions and metrics and aggregate functions.
There you go. Multiple dimensions, multiple. Okay.
Correct. Yeah.
That makes it difficult to visualize. I mean, this is a podcast; we won't be showing diagrams, but there's a StarTree index diagram I always use, and I always go in terms of just one metric because then the tree is very easy to show. But anyway, walk us through it. So give us an idea of you built a test. Tell us
Yeah.
about the data and the queries,
Sure.
and just take us through the story.
Yeah, so I thought, like, we've done it so many times over the different customers use cases that we've been onboarding, right? So I thought it might be useful to kind of run a test of our own, have it ready handy, right? Like that was the main motivation behind the blogs that I ended up writing. So for this blog, basically, for this test, what I did is I onboarded a New York taxi data set, has about 633 million records in there, like maybe around 6 year time frame, uh, and has like dimensions like, to pick up location, drop off location, and then also metrics around uh, what's the revenue for every trip that happened through that, in that city, right? Like, what is the duration taken for each trip, what is the revenue or the fare that was collected, and what was the distance that was traveled for that trip. So now this is a pretty wide, or a pretty large data set, over 633
Mm-hmm.
million records. And I thought I'll run some a group by aggregate query around different dimensions by day, month, and year kind of granularity, and get me. The idea was to run a typical aggregate group by query on this data set on a simple like 1 4 vCPU server and a 2 vCPU broker. It's a pretty tiny footprint, to be honest.
Yeah,
And
that's a small cluster.
yeah, and then like that too, right? Pinot is a distributed system. So in this, for this test, what I did is just one server and one broker, and then let's see what kind of throughput we can get, achieve out of this, what kind of latencies we can achieve out of it, right?
And you said 630 million records. About how big was the data, just in terms of bytes?
Data, it was a Parquet data, and if I remember correctly, the data size was, let me just bring up my notes and see if I have it captured. Yeah, it was about 10 gig.
Oh, okay.
Yeah, and then like Pinot compresses really well. Like with Parquet, I would say it's still 1 to 1, but JSON or CSVs are compressed, like we are able to achieve like 90% compression
Oh
in
well,
Pinot.
nice.
Pinot being a
Okay.
columnar data store.
So, New York taxi data, and tell us about. You said you were grouping by day, and your dimensions like distance and fare and things like that. Keep that.
Yeah, yeah.
Yeah, keep
So
going.
let's say, like, so my query pattern that I wanted to run was like, give me a breakdown by day for it for one full year. So I would expect like 365 different rows in my data set,
Okay.
and that would give me metrics around how many trips were taken on a given day, what was the total fare collected on that day, aggregate across all trips on that day, how many passengers were on the trip, and what was the distance traveled as well, right? So like three different metrics, and I could also have average, min, max, those kind of aggregate functions as well.
Yeah.
But that was the query. The query pattern was going across 365 days, which was about 146 million docs, right? So first iteration I ran, so I'm going to just walk you through the first part of the block series where I went through like three iterations. Iteration one, I just ran through like raw table scan without any optimizations, where I was transforming the date, like that was being captured in epoch milliseconds, into
Oh,
day
okay.
level
Okay.
granularity. Yeah.
Okay. So the the absolute worst thing you could do if you were
Yeah,
some
yeah, just to show
competitive
the impact, right? Like, yeah,
competitive project and you were benchmarking, you'd configure Pinot this way. So it's just as bad as it could possibly be.
yeah.
Yeah.
So with basically no optimizations whatsoever, just it's laws of physics, right? To
Yeah.
scan through 160 million docs, a 4 CPU server, and build those aggregates around those 146 million docs on those 1 year time frame. Yeah, the query was taking like 2 minutes, right? Like that's
Okay.
insane, and not
Yes.
really user facing analytics.
Not
So
that's not real time. No.
yeah, not at all, right?
No.
And not user facing also. So then iteration two, what I did is one small optimization by creating another powerful feature that Pinot offers, is a derived column, right? So where I what I did is at the ingestion time, I created a derived column to transform that epoch millisecond date into actually YYMMDD date, right? So now what that gave me is a great advantage, because now the basically uh, cardinality of that derived column was much lower than the original column. So now I could
Okay.
easily
So
use inverted index there.
got it. So basically a string that's like an ISO 8601 day, but just the day. So like,
Just the day, yeah.
yeah, 20101020, just something
Correct.
like that. Yeah. Okay.
Yeah,
Okay.
yeah. So now, because the cardinality is pretty low, right?
How many do you recall how many years the data set spans? I think you said so, but I don't recall what you
Yeah,
said.
it spanned across 6 years,
6 years.
2015
Okay.
through
So
2021.
that's
Yeah,
roughly 2000 cardinality of 2000, 2100, something like
yeah,
that. Unique
correct.
values there. Okay.
That's correct. Yeah. Out of 633 million,
Yeah,
like there was
that's
only
better.
233.
You
Yeah.
can, you can make an inverted index with that.
Yeah. And there you go, right? Like the iteration 2 I ran with just inverted index. So it had to still scan through 146 million docs, but with the inverted index, the query ran like in 1.5 seconds, right?
Oh,
So from 2 minutes to 1.5 seconds. Still not ideal, but still like it. I mean, a typical OLAP query pattern or user facing analytics is generally around like a year. Year is a decent time frame, but you could have smaller time frames. So you're not scanning through 146 million, but this was like a worst case scenario, right?
yeah. No,
And
no, you don't want to be scanning through all those documents. You would like to be able to prune that at some point. And
correct.
that's always the name of the game is to scan less, because you can really only scan so fast once you're scanning. So,
Yeah,
okay. Okay, good. Good. Again,
yeah,
I also wouldn't call that user facing or real time, but it's
yeah,
definitely the right direction. So,
yeah.
inverted index was helpful.
Yep, absolutely. And then I said, okay, now let's create a StarTree index. So I ended up obviously applying a StarTree index config on the table, where I had like date, month, year as dimension derived columns added into it. And the blog will walk you through the
Sure,
how
the
to configure
specifics
it
and
and
the
all that.
actual
Yeah,
what the JSON looks like and everything. This is the podcast version for your listening pleasure, and we will link to the blog posts in the show notes, absolutely. And you should go read those, everybody. If this sounds like a compelling index, you need to go through all the details that Sandeep has for you in the blog posts. So anyway, yeah. So
yeah.
you added
So
year, month, day as derived columns.
yeah, derived columns added, starter index added basically, right? And the same query, no change to it, right? Like I just ran it. Like Pinot will intelligently use the right index for the query,
Mm-hmm.
and it picked up starter index. It had to scan through only 409 documents, because these are aggregate docs that at the ingestion time Pinot has built
Mm-hmm.
in that star tree, and then. Like the we were able to bring down the latency to 4 milliseconds, right? So from
Okay.
1.5 seconds to 4 milliseconds.
Okay,
And
that's real time. That I'm gonna say that if you have some app that's going to issue that query in response to me tapping on my phone, and it takes 4 milliseconds to execute the query, I'm going to say that's okay to make me wait for that.
yeah, and then I mean I thought, the story doesn't end here, right? Like, I mean, this is obviously, it's not rocket science. It's a very intelligently built index, and really commonly popular for like OLAP aggregate group by queries, especially in user facing analytics scenarios. What I wanted to do is like, like Now with this small 4 vCPU server, I thought, let's see what will happen under high load, right? Like, let's see how much concurrent queries I can this particular small footprint can provision me for this kind of query pattern. So in second block, that's what I ended up doing. I brought up another VM, installed JMeter client on it, and then started firing concurrent queries.
Gotcha. Before we get there, tell me a little bit about how the index is built. You've mentioned pre-aggregation. I want to make sure everybody understands that's what's going on here. That's how the index works. How, as much as we can without being able to whiteboard diagrams and things, how's it put together?
Yeah, so that's a good question. So you can think about, like, StarTree is basically, it builds a tree-like structure, right? As the data is ingested, now you say, let's say, for example, let's say day, month, and year, kind of these are the three dimensions you want to aggregate on, right? So you will define it in a descending order of cardinality. So obviously, uh, cardinality for day column is higher than year and month, so you'll start with day column, I guess, right? So
Okay.
then you will so for each dimension in that dimension split order, it's going to start building like for each dimension value. Now it's going to maintain a mini tree of its own. Like, it has a specialized node called star node, which has the answer for you already, like, for that, right? Like, it's saying that for that particular dimension, for day equals so and so, uh, uh, it's building that. It has the answer for you, and then it's gonna apply the same algorithm over. Like, the way you want to think about it is, like, it goes through this multidimensional sort. It will split on the column and create a node for each value of that, plus
Mhm.
raw document range, and then create a star node that contains aggregated docs after removing the split column itself, and
Oh,
that has the answer for you for that combination. And then it's just gonna iteratively do the same thing for until it reaches the split threshold. The concept of the split threshold is your that is the trade-off that it is allowing you to do. That, by mentioning the split threshold, you're saying that I want to pre-aggregate up to certain number at certain level, and beyond that I want to resort back onto the raw docs. So that way you're making that trade-off between latency and
space.
storage there. Yeah.
Yeah. Okay. So if I could imagine that tree, the root node, and you said that you can have an arbitrary number of aggregations and metrics. So we're going to store those in the node, and the root node would be like the total fare and total distance traveled for the whole data set.
Yeah, the entire one.
And then under that, we pick the highest cardinality dimension, which in this case would be day, if we have year, month, day, obviously. And so there's 365 or 366 nodes under there. Each one of those is, well, how's that work then?
So now for that day, like,
Yeah.
so at that level one, you have exactly what you said, right? 365 days, let's say, right? And then there is additional star node. So that star node will hold the answer for the entire data set, like you were saying.
Yeah.
Now let's say day equals whatever 2015 January 1st, right?
Yeah.
So on that particular node, now it's gonna go
It's
further
day
down.
one. Yeah.
Yeah. So it's gonna go down to the next dimension in the dimension split order, which is
for us will be month for our data
month.
set.
Correct.
Okay.
Yeah.
So then that one day equals one has 12 nodes underneath it.
Correct.
Okay. And do you also put a wildcard node there if, like, say you put day and year, but you don't have month? Now that would be weird. No, that wouldn't be weird. First of the month, if no matter what the month is, you're interested in that. Can you have like a wildcard node? So if month doesn't show up in your query, you put a star node there, right?
Yeah.
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 Okay.
Absolutely. Yeah.
Okay. And then under each one of those, you've got however many years are in the data set, you've got nodes for those. And at every node, you actually have the answer, the computed aggregate that is stored there.
Yep.
Okay. And that's the magic. Okay. Okay. And this gets built during ingest. So
Yeah.
okay.
Yeah, it happens. If you want to get to the little more details, like while we are ingesting, obviously we are ingesting from a real-time source, let's say, right, or a offline source or a batch source. But let's talk about real-time source, for example. Uh, as the data is getting ingested, it's all staying in memory, right? And then at some point we will meet a segment flush threshold, and then that's when we persist that segment to the disk, and that's when we actually generate this index.
Got it.
Yeah.
And I can't remember offhand if we've had an episode where we've talked about this with Pinot. I'm going to need to look, and we'll link to the episode if it exists. But very briefly, what Sandeep just described there is when Pinot is ingesting from a streaming source like Kafka, it's writing stuff to disk, right? It's creating segments, which are the units of storage for Pinot that contain data, the raw documents, and the indexes, including the StarTree index. So it's writing segments, but when it's ingesting for a while, it's got this thing called the consuming segment that's in memory. And that doesn't have the StarTree index built on it yet until it gets written. But then it's in memory. So, and it's relatively small.
Yeah.
So you can just do your thing, do your scan everything there. Okay.
Yeah, and then average segment size is only like our recommended is like 100 to 500 MB, right? Only that much of data stays in memory, and it's already fast anyway, like serving from that. But the majority of the data is sitting on the persisted segments, right? And that's where you'll see the value of StarTree.
Got it. Okay. Well, that makes sense. I can kind of picture that. Now, you were starting to talk about throughput, and I stopped you, and I was interested in how it's put together. Let's get back to that. Tell me about throughput.
Yeah. So then I thought, like I brought up a VM, I installed a JMeter client, and then I thought, let's see what I can get. And then I also wanted to compare how it performs, compare it against inverted index as well, right? So, and then this time what I did is I kind of because we know like 1.5 second for 365 data uh, uh, on that 365 data, right? So we would get less than one throughput there. So what I did is I said, okay, let's go with a more commonly used query pattern, let's say 7-day time frame. And so even with that, the query had to scan through millions of docs, right?
Okay.
And then so first iteration I ran it with inverted index, and like for a 7-day query, 7-day query spanning across 7 days.
Uh-huh.
And I was able to get a QPS of 27, like that is 27 queries per second. And like
this is on the one broker, one server, 2 vCPU broker, 4 vCPU server.
Yeah.
Okay, so modest and small, but a baseline 28. Okay.
Yeah, and then P90th latency was 592. Like that meant, there was a marginal impact on performance with the throughput coming in.
592 milliseconds was P95.
Milliseconds.
Okay. So that's a decently high. Okay.
Yeah, decently sized, right? Still, user-facing analytics, you can still call it. It's sub-second, and the server
it's sub-second, but I don't feel good about it.
Yeah. Yeah, I mean, we were stressing the system as well. The server was, additionally, like server was at 100% utilization in terms of CPU. And then broker was at 5% only. So what that meant is like server was doing the obviously heavy lifting of processing the queries,
usual.
Right? So we had maxed out on server, so probably not a sweet spot configuration, like because we are stressing out. So we could have optimized for the latency by compromising for a little bit of throughput there. Maybe about 20 QPS could have gotten us to 90% CPU utilization and would have gotten us much better latencies. But that's where I stopped at that iteration. Basically, I didn't bother optimizing for it further. Because we wanted to.
You have one left, one important optimization step left, and that's the StarTree index.
StarTree index, correct. Yeah. So then iteration 2, I ran the same query, just made sure that there is a very easy way to, I mean, even though Pinot will pick the right index, like if StarTree is configured, it's going to use it by default. There is a way to, tweak it or tell Pinot not to use StarTree index, which is kind of counterproductive, but for troubleshooting purposes, right? Like in this case, I had passed that parameter to not use, and in this in the iteration 2, I said, okay, let's just use starter index, and with that I was able to get a throughput of 700, like 685, sorry, 685 qps,
Okay.
p90th latency of 140 milliseconds.
Okay.
Server utilization was only 20%,
Do you?
right? So
Okay. So the server now is down to 20% at that.
20,
Do you
yeah.
happen to remember what the median, the P50 latency was? Is that documented?
P50, I didn't capture it actually.
Okay.
I
Okay.
don't have
That's
it.
yeah, and that's not typical to do. I just my lower standards.
Yeah, P90th. Yeah, 90th is something that generally.
That's the one we're reporting. Yeah.
Yeah, and then other thing was like broker had reached like 100% utilization there, right?
Oh,
So
okay. So you are maxing out the broker now,
broker,
and
yeah.
the
So
server has much less to do. That's nice. That's
yeah.
hey,
So server could get
shoes
could
on the
take
other
more.
foot.
Yeah.
For once, the broker can or the server can look back at the broker and ask it to catch up. This is a good day for it.
Yeah, absolutely. And then at this point I thought, like I could really stop at this point because we had maxed out on the infra that we originally had.
Mhm.
But I thought, let's try and add more capacity on broker and see how much that server can handle with StarTree index, right? So that was the next iteration that I went through. And surprisingly or not, like I was able to get I think I added like 7 more brokers, so I had total 14 vcpus on broker, and still server had only 4 vcpus, and I was able to get a qps of 3500.
Okay. And that server, then that single 4 vCPU server was then finally asking for mercy. vCPU is hard to say over and over again, by the way. So it's a little bit of a tongue twister. Nice, though. I mean, that's an unusual configuration, of course, with all of those brokers and just the one server. But that's a good illustration of where the rate limiting factors get pushed around to when you've got a StarTree index and queries that are exclusively using that index on that table. My understanding is that you also wrote up a whole blog post on real life stories of people actually doing stuff that helps people and even could serve businesses and users using this table or this index. Nice.
Yeah, absolutely. Yeah.
Right.
So yeah, we can recap basically, or recap rather. We can. That's part 3 of the blog where I cover like 3 different use cases like that. We actually real production customer use cases, right? Where StarTree was able to bring a great improvement for the customer. Like one such was like ad tech use case, where they had like 1.8 billion records, right? Without StarTree, it had to scan 1.8 billion records, that particular query, and which was taking like 6 seconds. And with StarTree, it had to scan only 2300 records, so it's like 99.99% reduction in total doc scanned. And obviously the query latency came down to 15 milliseconds from 6 seconds.
Nice.
So
and that's
another 99% reduction.
And again, those are, so I will link to the blog post and refer you to that to read about more of those success stories. And I have to note, anybody listening to this who's more on the customer facing side of things, and Sandeep, you're a solutions engineer, so you're in a customer facing role. So I know all you customer facing folks are probably frustrated when I'm like, let's just talk about how it works. Use cases, whatever, just go read about that. They're very important. Okay, go read about them, please. We're just kind of at time here. And I'm glad that you documented those, because I think it's important for people to know, not only is this a cool piece of technology, and at the time of this recording, it's a thing that kind of sets Pinot apart from the pack in terms of other real-time analytics databases, But those numbers, like the crazy 15 millisecond query latencies and things, those are real things on real data sets. And he talks you through the size of the data and what was going on. And it's important to know that they're real and that you can actually deliver those when you need them.
Absolutely.
My guest today has been Sandeep Dabade. Sandeep, thank you for being a part of the Real Time Analytics podcast.
Thank you, team. Thanks for having me.
And there you have it. If you feel compelled to help us spread the word and grow the real-time analytics community, you can give us a rating on Spotify or Apple Podcasts or wherever fine podcasts are sold. If you're watching us on YouTube, hey, subscribe and, of course, hit that notification bell. And you can always share your favorite episodes on LinkedIn or Twitter or wherever it is you do social media. Thanks, and I look forward to talking to you in the next episode.